Hey guys, today we are going to graph piecewise functions. And piecewise functions are different equations used in different domains. And what it ends up looking like is a function or a graph that comes in different pieces. Okay, so we're going to graph these functions. First function has three different graphs. This f of x equals, that's function notation. It's exactly the same as y equals. And it's y equals 3, y equals negative 2x, and y equals x minus 3, but all in different domains. So the first equation is y equals 3, which is a vertical line up 3, but only in the domain of x's that are less than or equal to negative 1. So I'm going to put a little dotted line here. So less than or equal to negative 1 means to the left side of negative 1, and it's y equals 3. So it's this horizontal line right here. It can equal, it's less than or equal to negative 1, so I'm going to close a dot there and draw this horizontal ray that is up 3, but only graphed less than or equal to negative 1. Okay, then there's another portion of a line here that's negative 2x, so that's plus 0. It's going to have a y-intercept of 0 and a slope of negative 2. But I can only graph it between negative 1, which we've already put a dotted line for, and positive 4, which is right here. So the domain is only from negative 1 to positive 4. So I'm going to graph my y-intercept, and then just follow my slope, negative 2, so that's down 2 and left 1, and that puts me on the boundary on the left side. And it says greater than, not equal to, so it's going to be open right there. And to keep a negative slope, I can go, you know what, I didn't keep a negative slope at all, so I actually graphed the wrong point there. So let's get rid of that spot and try that again. So I had a negative slope, which means I go down and right, down 2 and right 1. And then down 2 and right 1 again, and down 2 and right 1, and down 2 and right 1, and that puts me on this boundary of 4, and it's less than or equal to, so I'm going to close a dot there. And then up and left keeps that negative slope, and I'm on my left boundary where it is less than but not equal to, so that will be open. So that is the second portion of my line, or of my function. So then y equals x minus 3, but only for x is greater than 4. So this line here and to the right. I still have to start at my y-intercept of negative 3, but I can't actually graph it right there. So I'll follow the slope, which is up 1 and right 1, and again, and again, and again, and now I'm at that boundary where it says greater than but not equal to. So I started at negative 3, up 1 over, up and over, up and over, up and over, and right there on the boundary it is open because it is not equal to. And then I continue up 1, over 1, and that is the third part of this function. Now, is it really a function? Will it pass the vertical line test? Well, if I draw a vertical line right here, it touches the graph here. Here, it's not touching the graph because it's an open spot. So it passes the vertical line test there. And same here. It's not touching anything. It's still not touching anything right here. As I go down, now it touches part of the graph. But there's no place where I can touch the graph twice. So this is a function. So y equals x plus 3, but only for x is less than or equal to negative 3. So there's negative 3. I've got a y-intercept of 3, so I'm going to start here, but I can't graph until I am left of this boundary. The slope is 1, so I'm going to go up and over, but I'm actually going away from my boundary. So instead I'll go down and left. And now I'm at the boundary, and it is less than or equal to, so I'll put a solid point there, and down and left, maintaining my slope all the way through the graph. So there's the first part of this function. Next is y equals negative x, so that's plus 0. I've got a y-intercept of 0. And I'm graphing from negative 1, so I'm just going to have an open space in here, up to 4. So a y-intercept of 0, and that's inside my boundary, so I can graph it. And then negative 1 means down and right. And I am less than or equal to 4, so I can keep that as a closed dot. And then up and left, and it is greater than negative 1, but not equal to, so that one is open. And there's the second part of the graph. And then for all x's greater than 4, so this boundary here, y equals negative 5. So it is a horizontal line down 5, and it is greater than but not equal to, so we're open there. And that's our third part. Okay, next is an absolute value. Okay, so there's a couple different ways we can go about this. One, we could just make a chart. We'll learn a third way later on in the course. So if I put in 0 for x, the absolute value of 0 is 0, minus 3 is negative 3. So I get 0, negative 3. If I put in a 1, the absolute value of 1 is 1, minus 3 is negative 2. The absolute value of 2 is 2, minus 3 is negative 1. And I could keep going like this, and it looks like I'm just going to have a line here. But if I go back to negative 1 for an x value, the absolute value of negative 1 is 1, minus 3 is negative 2. Looks like I actually went down a little too far on all of these. So I need to regraph those lines correctly. So negative 1, negative 2, and now it's made a different shape. Every time you see absolute value, you should get a shape of a V. So now I've got my slope established on this side of the V and on this side. Okay, so we've got a piece here and a piece here. It could also be written like this. So I would have a line over here of x minus 3, and over here, negative x minus 3. So on the left, negative x minus 3, but only in the domain of x's that are less than or equal to 3. Or 0, for x is less than or equal to 0. And then the line x minus 3 right here, but only for x is greater than or equal to 0. So that's how it could be rewritten like the ones above. Most people tend to like just to make that chart though. So if we put in a 0 here, 0 minus 3 is negative 3, and the absolute value of that, this time the absolute value is on the outside, the absolute value is 3. If I put in a 1, 1 minus 3 is negative 2, the absolute value is 2. If I put in a 2, minus 3 is negative 1, absolute value is 1. If I put in a 3, the absolute value, I get absolute value of 0, which is 0. if I put in a 4. Minus 3 is 1. The absolute value of 1 is 1. And now it has changed directions, and I've got the V shape that I'm looking for. The notation did not show up on here for some reason, but it should look like this. And the same here. Okay, and what that notation means is the greatest integer that is less than or equal to x. Okay, so if I make a chart like I did on the previous page, I'm going to make this x side a little bit wider. And you'll see why in a moment. If I put in, let's say, -1 for x, what is the greatest integer that is less than or equal to -1? Well, that would be -1. -1 is equal to -1. Minus 3 is -4. Okay, so when I put in -1, I got -4. Now if I go over a decimal amount, say I go over 1/2 to right here, so I'm putting in -1/2. What is the greatest integer less than or equal to -1/2? Well, that slides me right back to -1. So if I put in a -1/2, the greatest integer less than or equal to that is -1, minus 3 is -4. So even at -1/2, I'm at -4. If I put in -1/10, so I'm just like right about here, the greatest integer less than or equal to that is -1. Minus 3 is -4. So any fraction that I put in between 0 and -1 is going to slide back to a -1 because that's the greatest integer less than or equal to it. And when I subtract 3, I'm going to get -4. Until I put in a number as big as 0. Because now the greatest integer less than or equal to 0 is 0. So from -1, inclusive, all the way up to 0, but not including 0, I get an output of -4. So not including 0. So from -1 all the way to 0, but not including 0, I got an output of -4. So on that domain, my output is -4. So if I put in a 0, the greatest integer less than or equal to 0 is 0, minus 3 is -3. If I put in 1/2, the greatest integer less than or equal to 1/2 is 0, minus 3 is -3. If I put in 9/10, the greatest integer less than or equal to 9/10 is 0, minus 3 is -3. All the way up until I get to the number 1, but not including 1. Because once I get to a 1, my output changes. Because the greatest integer less than or equal to 1 is 1. Minus 3 is -2. So from -3 all the way up to, but not including 1, I had an output of -3. Once I got to 1, I got an output of -2. If I went up to 1 and 9/10, 1 and 99/100, greatest integer less than or equal to that is 1. And I'm going to get an output of -2, all the way up until I put in an input of 2. So you can now see the pattern so we can finish the graph. Okay, here, if I put in an input of, let's just use -1 again like we did on the previous one. This time, I'm doing my addition, then finding the greatest integer less than or equal. So -1 plus 3 is 2, and the greatest integer less than or equal to 2 is 2. So at -1, I got an output of 2. If I put in -1/2, okay, so and I add that to 3, I'm going to get 2.5, and the greatest integer less than or equal to that is 2. So when I input 1/2, I ended up with an output of 2. If I go all the way to 0, say I put in a 0, plus 3, the greatest integer less than or equal to that is 3.
Teachers, pardon the interruption. We have had a couple athletic events canceled.
So when I put in a 0 plus 3, I get 3. Greatest integer less than or equal to that is 3. So once I put in a 0, I have an output of 3. So from -1 up to, but not including 0, I had an output of 2. Starting at an input of 0, I have an output of 3. All the way up to, but not including, a 1. Because if I put in 9/10, I'm going to get 9/10 plus 3 is 3 9/10. Greatest integer less than or equal to 3 9/10 is 3. But once I put in a 1, it's going to change. So that shows us our pattern.